Okay, well, without further ado, let's get
Amazing.
going, Lisa. It's all yours. So here you go.
Perfect. I'm going to share my slides. Okay. Can you see this, Christian? And
I
can
can. Go ahead, please. Yes.
Can you see my cursor? Just checking.
Yeah. Yes.
Okay. Oh, all right. So as Christian mentioned, I'm going to be talking all about black holes today. And in particular, I want to talk about how we can listen to black holes using something called gravitational waves. And don't worry, I'm going to explain a little bit about what those are if you haven't heard of them before. They're very exciting, and I'm a huge fan. So let's get started. Okay, so I think it's really important that we begin with just a little brief interlude about what general relativity is, because that will be important for understanding what gravitational waves are and what black holes are. And then we're going to talk about what black holes are, which are my favorite astrophysical objects. And finally, we're going to combine those two together and see how we can use general relativity to learn about black holes. Okay. Okay, so let's start with general relativity. So many of you will have heard of Newton's theory of gravity, of course, but just as a reminder, it's a theory that says that if you have two masses, you just multiply them together and divide by the distance squared that they're separated by, and multiply by your lovely little gravitational constant. And this gives you the force, the gravitational force between those two objects. So this is Newtonian gravity. It's beautiful, it's elegant, it's very simple, and it does a great job describing a lot of the things we see on Earth. And famously, Newton is supposedly thought of this when an apple fell on his head. I don't know how true that story is, but this is apparently his great epiphany. And you know, it's a great theory. It's a wonderful theory, and it works very well in many, many cases. But for the type of objects that I'm going to be talking about, which, like Christian said, are very extreme, we're going to need to use something a little bit different. And that is, of course, Einstein's theory of gravity. So Einstein also had an epiphany, and he realized that gravity could be represented as the geometry or the curvature of something called space-time. And he called this theory general relativity because it was a generalization of his theory of special relativity. And don't worry, I'm going to explain this a little bit more. This might not mean very much to you right now, but let's first focus on this word space-time. Well, you know, what does that mean? Okay. So space-time is essentially sort of exactly what it sounds like. You have 3D space and you have time, and you basically mush them together, and that's something called space-time. And 3D, so that's 3 dimensions of space, and 1 dimension of time leads to 4-dimensional space-time. So space-time is 4D. And I'm showing you here the sort of 3-dimensional space cube. So space is gridded up in these 3 dimensions. And the key thing I want you to notice is that it's kind of flexible. It kind of can move around and stretch and squeeze. And this little yellow ball is maybe a mass, maybe an astrophysical object, and it's causing space-time to stretch and squeeze as it moves around. The other side to space-time is that each of these little points in space, you also have a time. So you have all of these little clocks, which hopefully you can see, and you'll notice that they're moving, the hands are moving at different rates. So for each point in space, you have not just your 3-dimensional space coordinate, but you also have a time coordinate, and time can be different across the entire space. Okay, so hopefully that clarifies what I mean by space-time. It's this 4-dimensional structure combining 3D space and time into 4D space-time. Okay, so what does this mean in the context of gravity and astrophysics? Well, Einstein's wonderful and very important theory basically tells us that matter, so like, physical objects like our Earth, for example, will tell space-time how to curve. So you'll notice I have a little Earth here, and space-time is kind of dimpling around it. It's sort of getting stretched, and that's due to the mass of the Earth. Similarly, we have the sun, and then you'll notice that the sun is much more heavy than the Earth, and so space-time is stretching even more due to the heaviness of that body. Then on the other side, space-time tells matter how to move. So as these masses stretch space-time, this will change how all of these astrophysical bodies move in the space-time. So it's sort of this feedback loop, right? It's, it goes both ways, and it's kind of nonlinear, and it's very complicated to deal with. But this is essentially the picture. So we have all of the matter in the universe, and that will sort of stretch and squeeze space-time, and then space-time will in turn tell all the matter in the universe how it should be moving around. And that's essentially the theory of general relativity. Okay, so now let's focus on something I really want to talk about in this webinar. And that is the fact that you can get these lovely waves that ripple through space-time. So what I'm showing you here is some kind of wave that is sort of stretching and squeezing matter in a wave-like fashion and propagating through space-time. So it's actually traveling at some speed through space-time. These are called gravitational waves, and Einstein hypothesized their existence. They're a consequence of general relativity. And we can use them to listen to the universe. So basically, we can use them to learn about all of the things out there in the universe, which is amazing. And it's something that's relatively modern in astrophysics. We've basically had a gravitational wave revolution in the past decade, really. So this is very new and very exciting science. Okay. So how exactly do gravitational waves affect matter? So I'm just going to give you a little toy example just to give you some sense of how they do this. Okay. So just imagine that you have a ring of particles, and these particles each have a mass. So they're each affecting space-time because they have some mass. This is the way the gravitational wave will affect them as they pass through. So there are two different types. There's this plus type, which is where you get a squeeze and a squish in sort of perpendicular directions. And then there's this cross type, where you get the squeeze and the squish in the shape of a cross. Hopefully you can see that relatively clearly. But this is happening in 3 dimensions. So, these things are propagating through space. So if you have not just one ring, but a series of rings, then this like gravitational wave will propagate through space in the way I've shown on that bottom blue diagram. So hopefully that gives you a little bit more of an intuition for how these gravitational waves sort of travel. They have these two varieties. And you can have superpositions of the two, combinations of the two. And they're called the polarizations of the gravitational waves. Okay. So now let's imagine that we don't just have a ring of particles. We have a whole bunch of particles, a whole bulk matter. So for example, on the Earth, we just have a whole bunch of mass sitting there, right? So how does that look when a gravitational wave passes through? It's going to look something like this. So everything sort of gets stretched one way and then squeezed, stretched the other way, squeezed, just in the same way as what was happening with the ring. And you'll notice I've put a little red L here, okay? And that's in allusion to what I'm going to talk about in a moment, which is how exactly do we detect gravitational waves? How are we going to measure them? And the way we do it is we have basically this L shape, and we want to see how much gets stretched in one direction and squeezed in the other direction. So how exactly are we going to do that? Because, you know, everything is getting stretched and squeezed, including us, as the gravitational wave passes through. So what's the mechanism that we can use to measure the gravitational waves? Laser interferometry. So if we send photons, or if we send light, lasers, down this L-shaped, this is something called an interferometer, and it'll help us measure the amount that the length the arms are changing as gravitational waves pass through. And so this is a laser interferometer gravitational wave detector, which is of course LIGO, if you've heard of LIGO. You have this characteristic L shape, and you see the arms change length, there you go, as the gravitational wave passes through. If you learned from physics about the superposition of two waves, you'll know that you can get constructive and deconstructive interference. So basically, as the waves line up or do not line up, they'll cancel each other out. So we can basically tell if the length of the arm is changing by sort of bouncing lasers from one end to the other. Okay. But that's essentially how we do it. And it's very clever, and it was invented by some very clever people, and it's kind of amazing that it can even work. And indeed, gravitational waves were detected for the very first time, or at least directly detected for the very first time, in 2015. And this, you know, was such an important physics achievement that it won the Nobel Prize. So Kip Thorne, Barry Barish, and Ray Weiss. So Ray is someone at MIT, actually, here with me, and they all won the Nobel Prize for this, you know, monumental achievement. So that probably made Einstein very excited, if he were to know. Okay. All right. So now let's talk about black holes, because I've told you about gravitational waves, but I haven't really told you how gravitational waves get produced. I've said you can use them to listen to the universe, but why? What produces gravitational waves? So spoiler alert, black holes are one of the things that produce gravitational waves in the universe. So I just want to tell you a little bit about what black holes are. So general relativity predicts the existence of these very strange objects called black holes. Essentially, you have some matter that undergoes complete gravitational collapse. So there's not enough pressure inside the object to resist gravity, and so everything just collapses completely to a single point. And this is a black hole. It's like the most compressed, most extreme thing that you can have in the universe. Basically, nothing is left that can overcome gravity. And so you have this total gravitational collapse. So what are the types of black holes that we actually see? So if you're an astronomer, and you're not just interested in hypothetically what, you know, general relativity predicts, and you want to know what do we actually see out there in the universe, we see these two types of black holes when we look out and try and find them. And they are little black holes and big black holes. And when I say little, I mean, you know, 10 times the mass of our sun, maybe 20, 30, 40, 50 times the mass of our sun. So pretty darn heavy. And when I say big black holes, I'm talking about even heavier. So I'm talking about millions times the mass of our sun, or even billions times the mass of our sun. So these are the two types. And some of you might be interested in the so-called intermediate mass black hole, which is something we know a lot less about. It's a little bit of a more mysterious case, so I won't touch on it too much, but that's the third type, and it sort of lies somewhere in the middle here. So what are these things? So we've got these little black holes, big black holes. Where do they come from? What are they? So the stellar mass black holes, the ones that are 10 times heavier than the mass of our sun, they form from stars dying. So you have really heavy stars dying, they explode in a huge supernova, and what's left over is this black hole, okay? Now, supermassive black holes, they are found in the center of every single galaxy that's moderately heavy, basically. You can find a supermassive black hole. So we have our own supermassive black hole, Sagittarius A star in the center of the Milky Way. And basically any galaxy you look at will have this big, chunky black hole in its center, okay? They don't form necessarily from the direct collapse of stars. There are many sort of hypotheses. It could be that in the very early universe, stars were much bigger, much heavier. And so the seeds of these big black holes started out really heavy, and then they grew and grew and grew as they, ate up everything around them. But it's still kind of an open question as to how exactly these really, really big black holes formed. But nonetheless, they're in the center of every single galaxy that we can see. Okay, so how do they form? Well, in this case, I'm really only talking about the stellar mass case. So as I've said, really heavy stars collapse in on themselves because they've burnt out their fuel. They don't have enough pressure to resist gravitational force. And so you get complete gravitational collapse after they've burnt out their fuel. And that's how you get a black hole. Now, there are two particular properties that a black hole has that you may have heard of. And the first one is a singularity. So when you think about something collapsing, basically without anything to push back, you kind of wonder, does mass become essentially infinite? So if you have essentially all of your mass compressed to a point, it does seem like the density of the black hole, which is mass divided by volume, becomes mass divided by 0 because you have collapsed all of your mass to an infinitely small point. You're going to get something like infinity, right? And the curvature of space-time is roughly equivalent to density. That's essentially Einstein's equations tell you that like density, energy, all of these things translate exactly to curvature. So you essentially get this region of space-time where everything is infinitely curved. And that's what I'm trying to demonstrate here. When we compare our sun, we have sort of a light curvature. Then we look at a black hole, we have this extremely strong curvature. And hypothetically, it becomes infinite right in the center of the black hole. There are some caveats to that, but this is essentially what a singularity is. Okay. Now, how about if you shine a flashlight on a black hole? So what happens if, you're standing on Earth, you shine a flashlight, as you'd expect, light sort of radiates outwards, travels away from you, that's sort of what you expect. On something like a neutron star, which is a very, very heavy star and has a lot of mass, you might see some curvature of those rays of light. Okay, so some of them sort of curve back down to the surface of the star. On a black hole, all of them curve back down. Light cannot escape from the black hole. And that is because the gravity is so strong that even light, even something that's, travels so quickly, cannot escape from the gravity of the black hole. And this is essentially something called an event horizon, which is the second property of a black hole that I want to tell you guys about. And it's a region around the black hole from which light can never escape. So if you're this little rocket and you're just outside the event horizon, then your escape speed is such that you're able to leave, okay? If you're inside of the event horizon, even if you're traveling at the speed of light, you cannot escape from the black hole. The gravity is simply too strong. You can't, unless your escape velocity exceeds the speed of light, you simply can't leave. So that's unfortunate. Okay, so in summary, this is the anatomy of a black hole. We have our central singularity, where we have infinite curvature, infinite density, crazy things like this. And then we have this event horizon. So inside of this event horizon region, light cannot escape. So this is the classic picture of the anatomy of a black hole. However, I'm an astrophysicist. A lot of you watching are also probably astrophysicists and have interest in astronomy. So let's look at a more complete picture. This is really what we see as astrophysicists. There's stuff around a black hole. They're really extreme, right? They have a lot of gravity, so they're going to attract a lot of stuff around them. And all of that stuff will also be very extreme. They have an accretion disk, which is just all of this matter that's spiraling around them. They have something called a corona, a relativistic jet. All of these things we can see with telescopes. Basically, the stuff heats up as it travels at relativistic speeds and produces light, basically. And so we can see it using telescopes. And that's how astronomers have learnt about black holes. So this is kind of the astrophysics perspective. We don't just have an isolated black hole with an event horizon, a singularity just sitting out there in the universe. There's always stuff around it, and we can use that stuff to learn about it. Okay, so this brings us to our first poll question. So Christian, if you could make the poll go live. So I want to ask you guys, how do you think that we can observe black holes? I've sort of given you a lot of hints here, but let me know. Which of these options do you think astrophysicists, astronomers can use to learn about black holes?
Very nice. So I launched the poll. Just a very quick question in between,
Yeah.
Lisa, because this is something that's always fascinating, because when you're talking about matter and space-time,
Yeah.
it's sort of like you said, matter influences space-time and vice versa, that we see the curvature. But what always puzzles me quite a lot isn't matter. Space-time doesn't exist without matter, really, because I can't imagine it. So isn't matter and space-time really the same because they're linked?
They're completely interlinked. Yeah, it's hard to even conceive of what it would mean to have just space-time without matter, without energy. There would be no way to learn about space-time. There would be no way to understand that coupling, that interaction between matter and space-time. So yes, I think they're deeply interlinked. Absolutely. Yeah. Okay. I think, yeah.
I'll share the results.
Okay,
so
perfect.
What do you think?
Okay, this is wonderful. So, so I basically told you that we can use gravitational waves to study black holes. I haven't quite told you how yet, but that is kind of the topic of the talk. So yes, a lot of people said gravitational waves. Other people said light emitted by the disk of material, the accretion disk that has formed around the black hole. That's also correct. So well done. As I told you, astrophysicists can use everything around the black hole to learn about the black hole by observing with telescopes, for example. Also, we can use orbits of surrounding stars to deduce that there must be a black hole somewhere. So we use that to learn about Sag-A star, which is our own supermassive black hole. And I think that was one of the Nobel Prizes recently, the year before last, I believe. But yes, so all of those answers are correct. Well done, everyone. But probably the most correct answer is all of the above, of course, because we can use all of these things to learn about black holes. So even though black holes are invisible, there are actually many different ways we can learn about them, which is kind of amazing. Yes, so all of the above. Okay, so these are the two ways we can observe black holes, roughly speaking. We can use light to measure the sort of the radiation produced by the accretion disk around a black hole. So we can point our telescopes at it and measure this spectrum. You might get something like a black body spectrum, and then you can learn about the temperature of this accretion disk and all of these types of things. We can also use gravity. So even if there's no light produced, anywhere near the black hole, we can still directly measure gravitational waves produced by a black hole, and therefore learn about the properties of the black hole. So these are, broadly speaking, the two ways we can learn about black holes. And both of them are incredibly fascinating and interesting, but I'm really going to focus on the second one here, gravitational waves. So now I'm gonna just give you a little mini introduction to gravitational waves and what kind of things produce gravitational waves. So if you just have a mass sitting in space-time, not doing anything, not spinning, not moving, doing absolutely nothing, does it produce gravitational waves? I'm going to give you the answer. No, it doesn't. It does not. Okay. And I know that these look like little Earths, and of course, Earth doesn't just sit there, it spins, right? So imagine that you had a perfectly spherical Earth. Earth is not perfectly spherical, but just imagine with me for a moment, we had a perfectly spherical Earth. So as it rotates, it's perfectly rotationally symmetric, and it just spins around. Does this produce gravitational waves? Again, no, it does not. Now suppose that we have two masses. So they could be stars, they could be black holes, they could be planets, and they're basically orbiting around each other. So finally, yes, this is something that produces gravitational waves. So what you need for a gravitational wave is, obviously, you need something that has mass, okay? And it needs to be accelerating. But it needs to be accelerating in a very specific way, so it can't have certain kinds of symmetries, because those symmetries will sort of cancel things out, and you won't end up with a traveling wave that sort of travels through space-time that we can observe. So if you have like perfectly spherically symmetric things that are spinning, that just isn't going to do it. You're not going to get a gravitational wave. So that brings us to our second poll. So let's see what you guys think. Which of these options does not produce a gravitational wave? I've given you a lot of hints here, so let's see how well you do. So I've mentioned some of these things. I haven't mentioned others, so we'll see what you guys think.
Looks like they're paying attention from what I see.
Okay, good.
It looks very good. Okay, we'll give a few more seconds then. Well, you're explaining it so well. It really is a pleasure. Okay, I'll end the poll and I'll share the results with you. There you go.
Amazing. Okay. Amazing. So keep in mind, I said what does not produce gravitational waves. So some people might have been tricked by that. So I'm saying what does not produce gravitational waves. So as I mentioned, if you have this perfect spherical symmetry and you have a star spinning, that actually doesn't produce gravitational waves. Luckily for us in the universe, there are very few things that are absolutely perfectly spherically symmetric. So if you have something like a neutron star, so I'll go ahead and give the answer here. Okay. So this is the correct answer. It doesn't produce gravitational waves. In the universe, most things have a bumpy surface. So like a neutron star, for example, which is a very heavy star, they have little mountains on their surface. So it's believed they have mountains on their surface. So when they spin, they have this bumpy surface, and that produces gravitational waves. Now, as I mentioned, two black holes orbiting one another, they do indeed produce gravitational waves, which is kind of, the reason why LIGO was able to detect so many gravitational waves, which is wonderful. A supernova, I didn't mention that at all. So if you don't know what a supernova is, it's basically this huge explosion that occurs when a star dies. And it's very messy. It's not symmetric at all. It goes in all kinds of different directions. It's quite hard to model, actually, but it definitely does produce some kind of gravitational wave because, there's lots of acceleration, there's lots of mass, and there's definitely not too much symmetry. Okay, amazing, but you guys did a fantastic job. Well done. Okay, so this brings me to the type of gravitational waves that I'm interested in, which are merging black holes, okay? So as I mentioned, if you have two black holes orbiting each other, this does produce gravitational waves. So that's awesome. All right, so we can learn about black holes, we can learn about gravitational waves, we can learn about general relativity, all from these types of systems. Okay, so what does it look like? Now, this is just kind of fun. So there's this huge gravitational field that each of the black holes have. And if you have enough gravity, this distorts the path of light. So things look a little bit funky. Hopefully this plays, yeah. So this is kind of roughly what you might see when you're looking at two black holes merging. Everything is very distorted. You can't see what's coming from, inside of the event horizon of the black holes because any light that has traveled in there can't escape. And then finally, the two black holes merge together and you're just left with a single black hole. Now that's kind of what it looks like. That's a simulation though. This isn't something that we've been able to film in reality. You've heard, of course, about the Event Horizon Telescope. That was a picture of a single black hole, not two merging ones. Okay. Now, this is what gravitational waves sound like. So you saw what the merging gravitational waves look like. And now this is what two merging gravitational waves, you've seen what two merging black holes look like. And now you're going to hear what two merging black holes sound like. So I thought I had a sound here. Maybe this. Okay. Could you hear that? I'm going to play it again. Oops.
Yes.
Yeah. Okay. So this is something called a chirp. So you'll notice that the frequency basically increases. So the pitch gets higher and higher and higher and higher and higher. And that is because as the black holes orbit each other, they get closer and closer and closer as they emit gravitational waves. And so their frequency gets faster and faster and faster. As they get closer together, the signal is also louder. So it should get higher in pitch and louder in volume, basically. And that's what we hear. And it sounds something like a chirp. So I'll play it again. Oh. Sounds like a little chirp. And that's what we call it. We call these chirp signals, basically. Cosmic chirps, so to speak. Okay. So now I'm going to show you what the gravitational waves look like as these black holes merge. And you can see the gravitational wave signal, like the amplitude of the signal down the bottom. Okay, so you see the two black holes and all of the red peaks and troughs. Those are the gravitational waves. So you can see how they sort of, wave and propagate away. and they get bigger and bigger and bigger. The amplitude gets bigger and bigger. They're also getting faster and faster, and then they merge together. And this is the merger. This is the loudest part of the signal, and also the highest frequency part of the signal is right when they merge together. Okay, so hopefully that gives you a little bit of understanding as to what I'm talking about when I say gravitational waves from two black holes. So let's just review what we've learned so far about black holes from gravitational waves. So as I've mentioned, we can use gravity to learn about black holes, and we can also use light. So in this little diagram here, we have some blue black holes, and those are black holes that we've seen using gravitational waves. This is actually very incomplete. There are a huge number more these days, but I just want to keep it simple. So we have, these are sort of the first few black holes which were detected by LIGO. Then we also have the purple black holes, and these are black holes that were detected using light. So they're, in particular, they're X-ray binaries usually. So you detect them using X-ray telescopes. And what you're seeing is basically the matter around the black hole heats up, produces light, and you can observe that. So these are sort of the two groups of black holes that were found. And you'll notice that the gravitational wave black holes tend to be a lot heavier than the ones which we see from X-ray binaries, or black holes that we see using X-rays, using light. And this is interesting. It sort of indicates that there are whole systems of black holes, whole types of black holes that we were missing by just using light to observe them. Okay, so it really fills in the full picture of all the different types of black holes in the universe, which is nice. And down the bottom, these little much lighter things are neutron stars, but I haven't talked to you about neutron stars very much, so we won't discuss those. But yeah, so basically as we go up this diagram, things are getting heavier. So all of these gravitational wave black holes tend to be a lot heavier, a lot chunkier, which is really interesting. Okay, so this is more like the full picture of what we've seen. And actually this isn't even complete, but it's a little bit more complete. So LIGO has had 3 observing runs, and each observing run, it observes more black holes. So they're starting to really add up. It's starting to get hard to fit them all onto one diagram. But once again, we have, basically you can see that you have 2 black holes that merge into one heavier black hole. So each of these systems is a binary with 2 black holes. They merge together and you get one heavier black hole. So as you go up this scale, you're getting heavier and heavier black holes. And there's one in particular that I want to point out here. So hopefully you can see how I've highlighted in red one of these guys here. So you can see it's kind of a light black hole with a heavier black hole. So you have something like, I don't know, 7 solar masses, 8 solar masses, merging with something that's like 30 solar masses. And this is the most extreme difference in masses that we can see on this diagram. Aside that there is another one, but could potentially be a neutron star. So we're not going to talk about this one. So I want you to focus on this little system. It basically has very unequal masses. So it has an unequal mass ratio. So you have a light black hole that's kind of 8 times the mass of the sun. And then you have a much heavier black hole that's like 30 times the mass of the sun. And this is a very interesting system. It's different to most of the systems that LIGO observes, which mostly have very similar masses with the 2 black holes. Okay, and I'm going to show you what this signal looks like. So you have the small guy and the big guy, and the small guy is orbiting around. Okay, they're producing gravitational waves. And one thing you'll notice about this signal is it's very long. So it's just going to keep going and going and going. And very slowly, the frequency is getting faster and faster and faster. It's getting a little bit louder, but mostly you just have that small guy kind of orbiting, chilling out, slowly getting closer to the larger black hole. Okay, so this is a very unequal mass gravitational wave signal. It's going to look something like this, okay? And basically you have this small black hole spending a lot of time in the space-time of the big black hole. It's spending a lot of time exploring, getting to know a lot of things about the larger black hole. And then finally, the two combine, they merge, and you have your classic merge, your classic chirp signal right here. Okay, and then they form a single black hole. So the reason why I wanted to point out this system to you is because this is kind of close to my own research, having a small black hole and a much heavier black hole. But as Christian mentioned at the start, I look at a much more extreme version of this. So the systems that I look at, you have a supermassive black hole in the center of a galaxy. And I told you guys, these are millions times the mass of our sun, right? So these are huge monster black holes. And then you have your little stellar mass black hole. It's not so little by human standards, but compared to the monster supermassive black hole, it's pretty small. It's a small guy, okay? So it's maybe 20 times the mass of the sun, let's say. So this is not just a slightly unequal mass ratio. This is an extremely unequal mass ratio. Nope. So you have a stellar mass black hole and a supermassive black hole. And now I'm going to show you what this looks like. So you remember the very, 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 very long signal that we just saw. This one's even longer. So this one would actually take in real time, it would take months to finish. But don't worry, you're not going to have to wait a month for the movie to end. But I just want to point out a few key features. We have the small black hole, which just looks like a little point relative to the big black hole. And it explores the space-time around the big black hole, with a huge amount of variety, like it explores all around, because it's just spending so much time orbiting. And these sort of pretty patterns you see, they're very close to the geodesics of the large black hole, if you know general relativity and you're familiar with geodesics. But if you're not, they're just the way that the small black hole orbits the big black hole. It orbits in these very complex, very interesting patterns, okay? And it spends a very, very long time orbiting around. So I'm just going to skip to the end. Okay, so now it's gotten a lot closer, very, very slowly. This is basically like the previous case I was discussing on the other slide, except much more extreme. So it takes a lot longer. It spends a lot more time orbiting the big black hole, and you have a much longer gravitational wave signal that's maybe months long or years long. Okay, and I think it's now finished, maybe. Okay, yep. And eventually it plunges into the big black hole, and you have, the same exact signal that you would with smaller black holes, but it's just a very, very, very long signal. Okay. So this brings us to this idea of a gravitational wave spectrum. So I think you're probably familiar with the electromagnetic spectrum. You have basically different types of light, which have different frequencies, different wavelengths. So as you increase in frequency to the right, you're going to get photons, I guess, with higher energy. You're going to get basically higher energy electromagnetic radiation. So I already mentioned X-rays, which is the type of light that you see produced around black holes. But you get a similar thing with gravitational waves. So smaller black holes, will tend to produce smaller amplitude waves that have shorter wavelengths, okay? Whereas larger black holes will have larger wavelengths, and they'll also have larger amplitude, okay? So this is now our gravitational wave spectrum. So as you move down this diagram, you get longer and longer wavelengths. Hopefully you can see that. So the squiggles get further and further apart. And the mass of the black hole increases as you go down, so that the type of waves that are produced by really heavy black holes have much longer wavelengths, okay? So up here I have LIGO, which is this L-shaped detector, and this is detecting stellar mass black holes. So that's what we currently have. We have LIGO, which are these two detectors in Washington and Louisiana in the United States, as well as Virgo, which is in Italy, and CAGRA, which is in Japan. So, but they all basically look like this. They're just these L-shaped interferometers, and they detect stellar mass black holes, so fairly light black holes, okay? Now, if you want to detect heavier black holes, you're going to need a different setup entirely. You're basically going to need something that's in space. You're going to need a space-based interferometer. And that is because you need the lengths of the arms of your detector to be extremely long in order to be sensitive to those long wavelengths of the gravitational wave. So really your only option is to put something into space. So this brings us to Lisa, which is also my name. And it's a very, very exciting future space-based gravitational wave detector. It doesn't exist. It doesn't exist right now. It's going to be launched in the 2030s. And it's basically LIGO in space with much longer arms. So LIGO has like 4-kilometer long arms. Lisa will have 2.5 million kilometer arms. Okay, so it's really quite different. It's going to have this like triangle shape, which you can see here, and it's going to orbit around the sun along with Earth. So we'll have a little friend orbiting with us. And yeah, hopefully we'll be able to detect supermassive black holes using this wonderful new space-based gravitational wave detector. So that's something I'm very interested in, and I hope to work on this detector or work on the data found by this detector in a decade or so, fingers crossed. So yeah, and that's basically the conclusion of this webinar. I hope you enjoyed it. So we learned a little bit about black holes and how they have event horizons and singularities. We learned how we can observe black holes using light and using gravitational waves. And then, you know, you let me indulge myself a little bit by talking about something that's very dear to my heart, which are these extreme mass ratio systems where you have a big black hole and a little black hole. And these hopefully will be able to provide us a lot of precise information because they just spend so long orbiting, and the gravitational waves are so long. So they provide us with a lot of information. And to detect these guys, we need to build LISA and send it into space. And yeah, that's it from me. Thank you so much. This was so much fun. Yeah.